rushing to do, turn that on, and I hit the wrong button. All right, we are recording again. Sorry about that. And, well, I thought we were, oh, I backed up. Okay. Now, maybe this time I'll get it right. We're not doing 12.7, in other words. 12.7 is cylindrical and spherical coordinates. If you need them, the section's there. But let's move on and do 12.6. And like I said, most of the time I include 12.6 with chapter 13. So that's what we'll do this time too. If I can ever get this to come up. There, I think we're close. All right. Now, don't let this first slide make you panic, okay? It almost makes me panic looking at it. What do we mean by quadric surfaces anyway? First sentence in this section. Quadric surfaces are the surface analogs to conic sections. What in the world do we mean by conic sections? Conic sections are based, have y'all had them anywhere? Okay. Here's your conic sections. Circles, ellipses, hyperbolas. That's pretty much it. Like one more. Okay. That's mostly it. Now, why do they call them conic sections? You know what a cone is? Okay, you use them in chemistry, right? Except they go both directions. A conic section, if you cut a plane perpendicular to the axis of that cone, then you've got circles. If you do it at a slight angle, you get an ellipse. If you cut this way, parabolas, that's what I'm missing. If you cut this way, you get a parabola, and if you cut this way, you get hyperbola. Okay, so those four shapes are your different things of a conic section. They call them that. Okay. Now, in 3 dimensions, you have quadric surfaces. This is the generic equation for any quadric surface. Now, what's quadric about it? Maximum exponent is 2. Okay? Now, the way they've written this one, this includes every possibility that you have in 3 space for these quadric surfaces. We're not going to do these. Here's what we're not going to do in general. We're not going to do any ones that have cross terms in them. What this would be if you had, well, this is our good old coordinate system, x's, y's, and z's. If you had a ellipsoid that started here and went through somewhere there, or started here and went through somewhere here and closed up, yeah, you're going to have x, y terms in them. We're not going to do those. We're going to stick with those who the axis is on one of the coordinate planes, coordinate lines. Okay, so we won't have any of these with the cross terms in them. X, Y's, Y, Z's, or F, Z's. Okay. And generally, we're not even going to have any of these. What that would be is an ellipsoid that is parallel to the x-axis. Its axis is parallel to the x-axis, but not on the x-axis. So basically, we're going to stick to ones that center at the origin. So we won't have any of these translate, this would be like remember back in pre-calculus algebra when you talked about translations, you didn't change the direction, but you just changed you didn't change shape, you just changed the placement of it. So basically we're not going to have these. So no, that's not quite true. We will use these in one instance, we'll use these terms. Only when we're missing one of those terms. Okay? Okay. We might use this one when that one's not there, or we might use this one when this one's not there, or we might use this one when that one's not there. Okay? We will use some linear terms, but only with this D. Most of the time, it's going to show up on the other side of the equation. That's your only constant here. Everything else has a variable with it. So this is your generic form of a quadric surface. We're not going there now. Basically, these are our quadratic terms here. Power 2, power 2, power 2, power 2, but we're not going to do these, power 2 and power 2. So those were the capital letters, coefficients, are your quadratic terms. Now, for this to be a quadric surface, at least one of those cannot be 0. 5 could be 0, 4 could be 0, but all 6 can't be 0, okay? And then it varies what those can be. All right. Now, like the conic sections, quadric surfaces are classified into small numbers of types. When the coordinate axes are chosen to coincide with the axis of the quadric surface, then the equation of the quadric has a simpler form. Like I was saying, we don't have any of the cross terms there. The quadric surface is then said to be in standard position. So we're going to stay with standard positions, basically centered at the origin, and with an axis along one of the coordinate axes. Okay. Now, before we do any more, I want you to remind me of the basic equation for a circle. You tell me the basic equation for a circle. If I ask you, you got, huh? Okay, simpler than that. X squared plus y squared is equal to r squared. Okay? That's the simplest equation for a circle, okay, of radius r. Okay? Now, I'm going to rewrite that one other way, sort of to make it a little more genuine. I mean, it's genuine, but uniform, okay? That's not quite the word I'm looking for. I'm going to divide every equation on both sides by r squared. That gives me x over r squared plus y over r squared is equal to 1. That's another very generic, probably more generic equation for a circle. Now, how would you do the equation of an ellipse? There's a couple ways to do that as well. You probably won't see this many places, but that would then be something like ax squared. Well, I'm going to give you the most general. I'm not going to go back and try to do one equivalent to this one. Here is the most general of an ellipse. Okay? X over a squared plus y over b squared, that's equal to 1. What's the difference you see here? They look pretty similar, don't they? It's a major difference. Okay, I'll sort of give you another thing here. The larger of A and B is usually called the major axis, and the other one's called either the minor or the semi-major axis. But different books call them different things. So, what would be the difference between a circle and an ellipse? In a circle, okay. Here would be a circle. r, minus r, right? With an ellipse, one of these axes is elongated, the other is not. Or this one's elongated and that one's not. Okay? So the major difference between a circle and an ellipse, they're both closed curves, but the difference is your axes are the same. X and Y different. X and Y axis there. Okay? The larger being the major axis. But other than that, they look just alike. So, in fact, a circle is a special ellipse where the semi-major and the major axes are the same. Okay, that makes a circle. So all circles are ellipses, but not all ellipses are circles. Okay. You want to do the others? Ones of these before we hit the quadratic surfaces? Does anyone know what a hyperbola's basic formula would be? It would be this: x over a squared, y over b squared equal 1. Only difference is a minus sign there. That makes a hyperbola. Okay? Now, that says there is a place where x is equal to a. But of course, then y has to be 0. For x to equal a, then y has to be 0, right? Because a squared over a squared is 1. And you can't subtract anything from that and get 1, right? So therefore your y would have to be 0. So basically, a hyperbola, x equal a plus or minus a, right? Here, but the y has to be 0, okay? And then from there on, you increase x's, and you have to also increase your y's so that the difference is equal to 1. So the x's increase and the y's increase to keep that difference to 1, and they both go both directions. So that gives you an hyperbola. You know, this is not the way to think of it, but it's the way my crazy mind works. If you took an ellipse, right, and flipped it out that way, that's not what's happening, but at least it gives you the appearance of what's happening. Okay, there's two more. I'll do the one I know you're used to. What's the basic equation for a parabola? Anyone know that one? Wouldn't that work? Okay. You can add some more terms in there and stuff, but remember, we're not going to deal with many of these cross terms or anything. That would be your basic parabola, right? Or x is equal to by squared. That could also be a parabola. It just goes on the other axis. Okay. Now, how could we write that sort of in our standard form here? I believe it would be something like this. Let's do x over a squared minus y. We could maybe put that over a b. I don't know if that's necessary. But that, I think, comes up being 0 then. Okay. Now, I'm not certain that's the best form to do it, so don't hold me to that. There's one other that we haven't done, and that's the cones. So we'll get to cones a little bit later. Okay? But just keep in mind these basic things. What would you have if you expanded a circle to 3 dimensions? Say again? Yeah, now you don't just have a circle on the board, but you have a three-dimensional circle. What would that be? A sphere. Okay? When you have an ellipse and you spin that around the major axis, you have a football. I mean, an ellipsoid. Okay? It's kind of like a football. Okay? American football. Okay? You already said sphere. Okay. Okay. For real football. Okay. Then you have hyperboloids, which would be this structure in three dimensions. And then you have paraboloids that look like half of those, but that's not really what they are in three dimensions. And then you have eucombs. Okay? And we'll get to those a little bit later. Okay. So, this is a picture of an ellipsoid. Okay? And this ellipsoid now has three axes. Of course, it's three dimensions. The longest of these is your major axis. In this case, the B looks like it's the longest by far. So that's your major axis here. But notice the A's and C's don't have to be equal. So that doesn't make a very good football. Okay? Footballs, you need those to be the same. Okay? But they're not here, so that's why it's not really a good football, but it comes close. Sort of a blimp-looking shape, except usually then even the two other axes are even. But they're not required to be an ellipsoid. Okay? Now, and the sum of all those is equal to 1. Okay? That's your standard ellipsoid. Now, if you had the A being longer, then the major axis would be along the long side would be along the x-axis. C, then it would be along the z-axis. It would be standing on the end. Okay? But this is just perfectly fine like this. Now, if you had those cross terms in there, you take this and twist it up this way or that way or something. If you had the linear cross term, that's just translation, keeping the same orientation. Then if you had both of them, you have a mess. But we're not doing that. We're going to stick with this form right here. Now, what I want you to think about and focus on are your traces. Remember, we talked about these in the last section. Give me an axis. A plane. One of your coordinate planes. ZX. Okay? The XZ plane right here. What do you have when you cut this ellipsoid with the XZ plane? What shape do you have? Not quite. It would be a circle if A and C were equal. If they're not, that's an ellipse. Right? And if A is equal to C, which in footballs and other things it quite often ellipse, it quite often is, but this isn't necessarily. It could be the A's are a little shorter here and the C's are a little longer, so you have an ellipse there. Okay? Now, anything parallel to the XZ plane, what will that give you? Smaller and smaller ellipses until you get out to B, and at y is equal to B, that plane, and by the way, the plane that's parallel to the XZ axis is those that are along y. Y is equal to 1, y is equal to 2, y is equal to 3, y is equal to negative 1, negative 2. Those are all the cross sections. Those traces are ellipses until you get to B, and then it's a point. Plus or minus B is a single point. Anything beyond that, there's no intersection. Right? All right, give me another coordinate plane. Which one? XY. Here's the XY plane. Okay, what do you have when you intersect that ellipsoid with the XY plane? This one goes through here, here, That's an ellipse also. Okay? This one definitely, the B is the major axis, the Y is the major axis, and the X is the minor. And if you did any Z is equal to 1, 2, 3, anything up to but less than C, or minus 1, minus 2, minus 3, or anything down to but greater than minus C, what would you get then? Ellipses also, getting smaller and smaller. And at Z equals C or minus C, you have a single point is that intersection. And beyond plus C or minus C, no intersection at all. So the one remaining plane would be the YZ plane. And what do you get when you do a trace of the YZ plane? That would be C to B to minus C to minus B and around like that. What would that be? An ellipse also. And any, if that's the YZ plane, then you're taking traces x equal 1, x equal 2, x equal minus 1, x equal minus 2, until you get out close to A or minus A, but not at those. You also get little ellipses, but they're smaller and smaller until at x equal A or minus A you have a single point, and after that you have nothing. So everything you cross that with, along a plane or a coordinate plane or anything parallel to a coordinate plane, you always get ellipses. No wonder this is called an ellipsoid, three-dimensional ellipse. Okay? Now, what you were just describing, the first one you said was the YZ plane, wasn't it? Okay? That's when x is equal to 0. And what is that? That was exactly the ellipse we had earlier. Or XZ plane or XY plane. Those are all ellipses in that plane or any Z. All you have to do is put Z equal 1 here, right? If Z was equal to 1, say, and 1 is less than C, so this gives you a number. Subtract that from this side, and that gives you 1 minus something, so that's a smaller number. Take that smaller number and divide here to get it back to 1, and you've just got smaller and smaller ellipses as you go out, as long as you don't let Z exceed 1, C, plus or minus. Okay. Got it? Okay. So here's the equation of the ellipsoid. They had it on the slide before, and they still have it. Okay. That is your basic equation of the ellipsoid. Okay. I think we're ready. Okay. Surfaces are often represented graphically by mesh of curves called traces obtained by intersecting the surface with planes parallel to one of the coordinate planes. That's what we were just talking about. Okay. Algebraically, this corresponds to freezing one of the three-dimensional variables, holding it constant, and then letting you go up or down or right or left or however from there. So let's do example 1. I think this figure relates to it. Describe the traces of this ellipsoid. Okay. They don't list it, do they? Boo, yes. No, that may not be the one. Okay. So let's, before we do, I think the one that we're looking for is at the bottom. Okay, so we'll do this first. So here we have the intersection of the plane Z is equal to Z0 with an ellipsoid, and you see this is what I was talking about before. I didn't realize I had this. This is also an ellipse. You not just the XY plane where Z is equal to 0, but somewhere where Z is a little bit greater than 0, like Z0, okay? So up here, that gives you another ellipse, okay? Every intersection of a plane parallel to your coordinate planes is another ellipse. We call that a trace curve, okay? Now, Goodness gracious, they're skipping. Okay. They've got the slides out of order. All right. Here's the. Oh, okay. What's that? The one what? The slides weren't in order. This is ellipse. The previous slide had gone on to hyperboloids. Okay, we aren't finished with the ellipsoids. So this is the last slide on the ellipsoid, and this corresponds to example 1. Okay. Now you'll see example 1 is describe the traces of the ellipsoid x over 5 squared plus y over 7 squared plus z over 9 squared is equal to 1. Okay? Now, what makes it an ellipsoid? Just looking at the formula. This is a 1, and just by everything we looked at so far have been 1s. Okay? But it is a 1, so that's one thing. The other thing is all these signs are positive. You don't see that, that means it's positive, that's positive, that's positive. All three of the signs that deal with the variables have to be positive, and it has to be a positive 1 on the other side. If you have that, you've got an ellipsoid, guaranteed. What's your major axis here? Z. And how far up and down does Z go? Yes, from -9 to +9. So 0, 0, -9 is on that. 0, 0, +9. From x is 0, y is 0, Z has to be equal to 9. Or -9. So -9 over 9 is -1 squared is 1. Okay? So yeah, those points have to be on there. So this is a lot like we did the three-dimensional planes. Remember? Set everything equal to 0 and see what you get. Everything but one thing equal to 0. And then your next more major axis would be your y, where x's and z's are 0, then you'd be at ±7. 0 -7, 0, 0 +7, 0. And then your most minor axis would be your x equals -5 or +5. So you've got those points down. I mean, those are really easy to do. So you can draw those curves in. In the x, xz plane where y is equal to 0, so you're not going up or back on y, you're going from -5, 0, 0 up to 0, 9, 0, 9, down to 5, 0, 0, down to 0, 0, -9, and that's that ellipse there. On the xy plane, that's where z is equal to 0, it goes ±5, ±7, that's the ellipse there. Now that sort of looks like a circle, but it's not. This is 7 units this way, only 5 units that way, so that's an ellipse. But even if it was a circle is an ellipse also, just a very special case. And then finally, when, which one haven't we done? This one maybe? No. Yeah, this one. When x is 0, then you're in the yz plane, and you're going from +7, +9, -7, -9. So that's the ellipse that you focus on. Okay? Now, not only are those ellipses, but as you go up, where z is +1, +2, +3, +4, any numbers in between there, you get smaller and smaller ellipses. It looks like here, that looks like the 0. Okay, it looks like maybe this z is equal to 2, 4, 6, 8, and then 9. And -2, 4, 6. You can't see the 8 there. So they're not quite copacetic here, but pretty close. Okay? Those would be what they call the horizontal traces. That's if z is vertical. Okay. You got two vertical traces, one along x's and one along y. The ones along y are your, what is that, magenta or pink or red or whatever. And y goes from 0 to 7. How many do they have here? 1, 2, 3, 4, 5, 6. Yeah, they look like, I did it right. 1, 2, 3, 4, 5, 6. So this must be 1. This must be 0. 1, 2, 3, 4, 5, 6, and 7. Okay. And then backwards, -1, -2, -3, -4, -5. You can't see -6 and -7 is behind it. Okay, that's a vertical trace, but also parallel to the YZ plane, those are vertical traces. Now they have 5 coming out here, and I can't tell where the first one is. Let's just say that's 1, 2, 3, no. This must be the first one, 0. 1, 2, 3, 4, 5. So these are your vertical traces this way, and it's really hard to see them behind. That would be 1. I can't make them out. 2, 3, 4, 5. Going back that way. I can see part of 1 here. Going back that way. It's really hard to see. Okay. But anyway, that's, you got 2 sets of vertical traces, 1 set of horizontal traces. If you set z always vertical, which is most of the time the case. So everything's an ellipse. Every trace is an ellipse. Okay? And that's basically how you set about drawing them, and then you just fill in the best you can. Okay. And then when you do these smaller traces, you're subtracting off, let's say, a smaller trace on x, so x equals 1, say, rather than 0. When you have the one at the YZ plane, x equals 1, then that would be 1/5 minus 1/5 would be 1/25. Subtract that from 1, you get 24/25. And if you were to normalize that by dividing through, you're already taking care of this. These numbers get smaller. Okay. Because you're dividing by something else. Okay. They sort of show that in the book a little bit, but not too well. Some of the things they don't do as well here. Let's move on to hyperbolas. Okay? I mean, hyperboloids. Okay. This one I had to go back in the slides to get. Okay. Now, I don't like it that they've lost the standard form here. In my mind, this would be better to do it like this. And I'm going to have to lose it to do it, but here I'll do it. X over A squared, Y over B squared, Z over C squared is equal to 1. Okay? A hyperboloid of one sheet is going to have one of these. The first one we usually assume is a plus. One a plus and one a minus. Okay? Now that gives you the same thing they have down here, but to me this is a much more standard way of expressing it, rather than moving the Z to the other side. Okay? Of two sheets, X over A squared, Y over B squared, Z over C squared, and you're going to have a 1 here. Okay. Now, you can do one of two things here. You can do it just like we did before, make this a plus, a minus, but then this becomes a minus. Okay? So that's one possibility. Plus, plus, minus, minus. Okay? That's just like the hyperboloid of one sheet, except now you have a minus 1. Okay? The way I like to do it a little bit better would have been this. X over A squared, y over b squared, z over c squared equal to 1. Leave the plus 1 there and put minus minus plus. That's still the same as this, right? Now we've moved the 1 to the other side, leaving this positive, but then have to move these two back over here with this one and make both of them negatives. So either, I don't care which way you do it. Actually, to me, this is a little more standard looking, okay? So a hyperboloid of one sheet is going to have one minus sign. A paraboloid of two sheets is going to have two minus signs. That feels good to me. It's easy to remember that way, and that's how I would do it. Now, I can't remember if I've ever seen a text do it, but it just seems like to me that fits really well, okay? All three positives with a plus sign over there, that's a hyperboloid, ellipsoid. If it's got one or two minus signs, that's a hyperboloid of one or two sheets. But everything else is just the same. So to put the minus one there just seems a little, discordant. Okay, it just doesn't feel right. This feels better to me. But if you like the other way, fine. Or if you like their way, fine. Go for it. I just have too many things to remember. I like it simple, stupid. One minus sign, one sheet, two minus signs, two sheets. Okay? So, however you like to do it. Okay? Now, what do we mean by this anyway? Well, let's pause a moment and see. What happens if z is 0? What do you have? You could do it here too. What does that describe for you if z is 0? Okay, isn't that just like an ellipse? Right? If that's 0, that's an ellipse, isn't it? Think back what ellipse was. Yeah, that's an ellipse. So when z is equal to 0, you have ellipses. Okay? That's what makes this one sheet. Because if z is equal to 0, you have an ellipse there. Okay? As you go up, the sheets get bigger. Okay? If z is something greater than 0, then you're subtracting something greater than 0, which would then be adding something greater than 0 here, so you're getting bigger and bigger ellipses going up. Right? If the z's are getting bigger negatively, when you square it, it's still getting bigger. You're subtracting a big number here, which would be adding a big number to move it over there, so it's getting bigger. So sure enough, this is what hyperboloid, where is it? They've got these slides so screwy. Here it is. That's a hyperboloid of one sheet. Small ellipse in the middle. The ellipses get bigger as you go up and down z. Or whatever your major axis is. The axis of this is the thing with the minus sign. Well, the thing with the different sign. I'll put it that way. Okay. So that's what you got there. Now, let's go back here and say, what would you have? What shape do you have? This is a plane figure now. Would you have if the y's were 0? Remember what we did at the very beginning, before we started these oids, the quadratic surfaces? We were doing the conic sections. Which conic section was that? That was a hyperbola. No wonder they call them hyperboloids then. So this, if the y is 0, then in the xz plane, you have hyperboloids going front or back. Okay? And sure enough, let's see if we can find it now. There. If it wasn't y is equal to 0, it's what I want to trade you on. Okay? Here's one. There's a red one here and a red one there. You can imagine another one in here and another one here. You have little hyperbolas that way. And this way. going back on y, yeah, okay. And guess what? So your horizontal trace here are ellipses. Your vertical traces are, where you get them, are hyperbole. And see, here the green one's coming this way, okay, along x. So again, if you let x equals 0, again, you have hyperbole, right? Okay. And then if you let that vary. All right. So that's your one sheet, okay? 1 minus sign when you put it in standard form with an equal 1 over there. This one down here are 2 sheets. Okay, what in the world do we have here? And again, my suggestion to you is to say the one with the off sign is your axis. Okay? And again, that's going to be z. But here we have a strange situation here. Okay? Let's just start with x as being 0. Again, this is hyperbolas, right? Y is equal to 0, hyperbolas. What in the world do you have when z is equal to 0?
I was going to say like upside down.
Okay? Well, think about it. This thing, because it's squared, is always positive. This thing, when it's squared, is always positive. Okay? And you have, when you negate the positive, it's negative. You negate the positive, it's negative. You have 2 negatives equal 1. No, no, no. You can't have 2 negatives adding up to be 1. Okay? So that's why you have 2 sheets here, because you have a gap in here where you don't have anything. You cannot have any values between plus or minus z. I probably should have pointed that out first. Okay? Because when z is equal to c, your x's and y's are zeros. Okay? Right? Gotta be. That would be 1, so x has to be 0, y has to be 0, right? That's the only place that's the starting point for z, either plus c or minus c. Plus c on the top, minus c at the bottom. Anything greater than that, z greater than c, yeah, that'll be greater than 1, so these can have values there. But you can't have z less than c, because then you're going to have something less than 1 here and negatives here. And that's not ever going to work. Okay. So, that's what makes the z, the off sign is going to be your axis, and that's going to be your plus or minus point. Where you begin. That's why you have 2 sheets. Okay, this hyperboloid is 2 sheets to the wind. No, never mind. That's not it. Okay. And now, that sort of describes it. There's something else that I think now would be a logical question. Okay? Is there some place here where now is the one time this form does make a little sense to you? Here that's equal to plus 1, here this equal to minus 1. Okay? Now, I can almost feel a question rising in someone's inner brain. It may just way to the surface here. What if that was equal to 0 and not a plus or minus 1? Wouldn't that be a good question? You know that x equals 1, you got a hyperboloid of 1 sheet, and if you got -1, it's a hyperboloid of 2 sheets. What if it's something in between? Like 0. Now let's see if that's going to be the next one. I think it is. Okay. Okay, no, they're going to do some examples first. So let's not go there yet. We'll back off from there for now and do example 2. Is this example 2? X, yeah, well, they've written it in their weird form. Okay. Now, that looks about as good as I want to get it, right? Okay. This is their way of writing it. A hyperboloid of 1 sheet. I would have written this x over 2 squared plus y over 3 squared minus z over 4 squared is equal to 1. Okay? That's going to be this one. Okay? And obviously, when z is equal to 0, that's an obvious thing here. These are all ellipses. Okay? And any z value you put in here are going to be bigger and bigger ellipses. So there's that first ellipsis. X plus or minus 2, y plus or minus 3, that's the smallest ellipse you're going to get. And then any z bigger, you're going to get bigger and bigger ellipses going up and going down. And if y is equal to 0, you've got a hyperbola here, and that's your y is equal to 0. That would be this reddish, magenta, pinkish, whatever you want to call it. That's that one from here to here. And when x is equal to 0, that's going to be your green hyperbola. I'd like to move this on this side and say y over 3 minus z over 2, that kind of stuff is equal to 1. That's going to be that. Okay? That look pretty reasonable? Okay. And this next one shows the other horizontal traces. Okay, and the other vertical traces. It shows a couple more here. They changed colors on this, didn't they? Yeah. No, they got it the same. The pinks are along the x-axis. Yeah. There's the first one here. No, I can't tell. No, they have. Yeah. But you see, they've just thrown more in than I would have guessed. Yeah, this pink one is here. That's exactly this one here. And then they've drawn more. As y gets larger and larger, right? Yeah, you get them like this. So it's really rather strange. You get hyperboles this way, and then after a while, you get them going like this and here. So you get hyperboles that way too. Only those look like they're on the y's are equal to constants, and the green one look like x is constant. Yeah, and indeed, this is the pink one here is where y is 0. Right? So the pink ones there are y at greater values than that. And then you get the green ones are when x is 0 here, and then x equals greater constants there, and you get these others. So aren't particularly easy to draw. Get those ellipses in there in the middle, and then the other things will fall into place. All right, hyperbola of 1 sheet. Now, are they going to do one of 2? I think they will. This is example 3. without numbers, okay? Boo hiss. I like them better when they have numbers in them, because you can't tell now what it's going to be. Now again, they wrote it in their way, which is perfectly fine, it's correct. But I would just written, notice here the y-axis is the axis of this thing. So your thing is this way. And if you wrote it, leave this alone, move this here, and these two there, then you have two minus signs for these, and a plus one left over there. So you have a hyperboloid of two sheets, okay? And now, here's the advantage of this shape. Certainly y has got to be greater than b, period. When y is equal to b, this is 0, so both of those are 0. So that's why y is equal to b has x equals 0, y is equal to 0, plus or minus b. That's where you begin these things, okay? And if y is any greater b than that, then this thing gets to be greater than 1, and now you have ellipses. Now these, your vertical trace or your ellipses here, just one of your vertical traces is, okay? Your horizontal traces are always hyperboloid. I mean, there is no hyperboloid. There's one horizontal trace, that's the green one here, and that would be when z is equal to 0, okay? Or z is equal to a constant. Z is equal to 0, you have the foundational green trace there. They got so many I can't tell which one it is. And then you have z's going up or down. You know, you've got those hyperboles too. But then x equals 0, same type deal. You would have this red one here that way, and somewhere here the red one goes through there. And then x is greater than or less than 1 will form these other hyperboles. Okay, so that's for hyperboloid of two sheets. Is it getting close to time? Oh my goodness, how could it be? Okay, we were just beginning to have fun. So, they didn't give us any numbers there, but we've done that. We will start next time in the elliptic cone. And I had already asked the question that we didn't get to answer, and we'll answer it next time. Okay? Let's see if we can get some more homework exercises here. I think you can do any of the odds 1 through 5 with no problem. And I think you're going to have to just can it there, because we haven't done the rest of those yet. Okay, so any of the odds 1 through 5. Good deal. Sorry, there's two programs for this one because I hit the wrong button before. So you